task or whatever you want to call it today. Yeah, today. So feel free to stop by. Homework's I like this homework problem set. I think it's fun. It's a little different. It's probably something you've never really thought about or played around with. And you're going to sit here and wonder why why it's in a chemistry class. Because there's not a lot of chemistry in this problem set, but you're going to see, as I say over and over again, these fundamental concepts about wave functions, deflection, like that, are embedded directly into the rules of chemistry. We just don't really quite have an ability to really talk about that perspective, those ideas from a chemical point of view yet, but we're getting there. After today, I think we can start to think about things. What we really want to do is figure out where an electron is, right? That's what chemistry is, about how electrons move from one object to another, how are they shared. We have to think about electrons in space, right? In a room or embedded in an atom. And so we're going to have to move away from vectors to start thinking about X, Y, and Z. I'm going to try to make that connection for you too. Just a heads up, I said this already today. You're going to hear this a lot. Maybe actually I have no idea. So I'm the kind of person, I talk about my wages and my salary. I know in some companies they don't like doing that. I don't care. I'm going to do it anyway. The president announced today that they turned off our retirement match for all employees. So that's effectively a 10% pay cut for all of us. So we're all kind of grumpy today. Just a heads up, just give a little bit of sympathy for your instructors and your staff members today. It's not an easy day for us. Despite that, I'm still here, and I still will continue to be here because I was talking to head of athletics recruitment today, a colleague of mine, and we said that even though we're underpaid and we're getting our wages cut effectively, we still get to have fun for a living, and that's true. And teaching quantum mechanics is what I wanted to do. This is my calling when I'm doing with you today. So I'm going to be here anyway, even if they pay me minimum wage. It's what I want to do with my life. So, but we'll be a little grumpier than we'll go this week. President's talking to all of us starting tomorrow. So we'll get all of our, they hire presidents to be punching bags. I mean, that's really what a president's for, is to be a punching bag. So he'll be a punching bag. We'll feel a little bit better and we'll go back to normal. You guys have been great, however. So it's nothing to do with you. You guys are doing great. You're not doing anything wrong. It's an administrative problem. Stephen Kaplan did some bad things to the school, and we're fixing them. So it takes time. Anyway, better things. Let's talk about things that we can control. Things that will always be here, unlike money. And that's wave functions and atoms and chemistry. We're never going anywhere. Chemistry is an ancient, even though chemistry has only existed since the 1700s, it goes back much further through alchemy. We're always going to be here. So we've talked about the wave function a lot this last few weeks. I hope I've kind of given you a sense of what a wave function is, which is very abstract, right? It doesn't really seem to have some sort of physical, it's not really something you can physically touch. It just gives you some sense of how to understand the results of an experiment, right? It's a way to encode the results of that experiment. So what I want to do is I want to expand that, and I want to tell you that the wave function is, it really is something that is, if you have a system like an atom, if you know the wave function of that atom, you've completely specified its behavior. You know every little detail about that atom. You know its wave function exactly, or a molecule. Okay, so there are pathways for us to construct wave functions using basis states. And one of the goals of this class is to tackle chemical problems and understand what that construction looks like. What does the basis states in a wave function for the hydrogen atom look like? You've seen those basis states before. You learned them in Gen Chem. They're the orbitals, 1s, 2s, p's, right? We'll see that. And so you have this kind of qualitative appreciation for this idea that an atom is constructed from energy levels, from orbitals. And we'll see the molecules are constructed from orbitals. And those are basis states, or electrons, orbiting some set of nuclei. Right? So there's a lot of physical meaning involved in this. We just have to tease it out. And one of the things that we've introduced last class was that this is only half the problem. Right? We have, for our deflecting silver atoms, we have a construction that allows us to talk about the atom but it doesn't let us talk about what's happening to the atom in the measurement. And that's what I introduced last class when we showed that the measurement device itself can be represented as a matrix, a vector of vectors. And I want to explore that a little bit today to focus on that part of the box part. We know what the silver atom looks like, but let's appreciate the box. And then what I want to do is once we understand how that box works a little bit more, to ask about what other boxes can we construct. Another question that we'll have to answer is each box gives us a piece of information about the atom, right? The Z box tells us only whether an atom is deflecting up or deflecting down. Right? Obviously, silver atoms have other properties, but that box is constructed specifically to tell us that one property. And then when we ask, okay, well, what about the X deflecting? And we saw that those are not compatible measurements. You Z then X, you lose the information about the Z. So do you, in some sense, redefine the atom from something that has Z properties to something that has X properties, and not both at the same time? So that's a problem. I mean, it's a good thing. We'll see that you can do something with that. That's an intricacy that we can take advantage of. But another question you might ask is, how do we continue to define properties of the atom? So we can define it based on X on the Z deflection, but is there some other property we can measure down the line that we can measure in a compatible way with Z deflection? X doesn't work. But are there other compatible measurements that can go along with this description of Z? And yes, there are. We'll see that. You may remember, let's give the example of the hydrogen atom. Again, I'm jumping ahead a little bit, but you guys have seen the electron structure of atoms before. And this idea of subsequent measurements that are compatible is inbuilt into the description of the atom that we make, the electronic structure of atoms, right? We fill electrons in orbitals. If you remember, we think about the orbitals of hydrogen. You have the 1s and the 2s and then the 2p's. You have the 3s, the 3p's, and the 3d's, the 4s, the 4p, the 4d, and the 4f's, right? And those fill up as you go down the periodic table, of course. Those labels, the 1 and the s and the d and the p, all correspond, each of those labels correspond to a specific compatible measurement that we can make for the atom. Okay, so the 1, the 2, the 3, the 4 correspond to a specific box. The S, the P, the D, the F correspond to another box that we can measure of the atom. And then if you remember, there are 3 p orbitals, 5 d orbitals, 7 f orbitals. And note that degeneracy, the fact that there are 3, 5, and 7, also come from another box that we can use to measure. So the hydrogen atom, the orbitals are constructed from a sequence. The way we construct the labels for the orbitals is for a sequence of 4 different measurements that are compatible with each other. Okay? So the idea is that we define a system, a wave function for our system, and we try to figure out what are the things that we can measure about it simultaneously. And the more things we can measure, the more we can define things. It also means that the more we can measure, the more complicated the system gets as well. Because the reason why it gets more complicated is because we have a series of compatible measurements. That's more things for us to measure, more things to define as properties of the atom. And so the atom gets more complex. It's just the way that we represent the wave function, the outcome of our measurements. If we can measure 4 things, let's measure 4 things about the atom. Let's define it as much as possible. And you can kind of imagine that that may be a kind of like a downward hill, you know, like a rabbit hole, right? That you can just keep going and adding more and more properties. It turns out eventually you run out of things that you can define. Okay, so there's a limited set of labels in some sense. And there's not an infinite set of labels. So that's kind of where I want to go, right? I want to think about what are these measurements, understand measurements more, and how do we know if they're compatible? And I'm going to teach you 2 important measurements that we'll do today that aren't deflection, that will teach this lesson of compatibility. Okay, so let's go back. Let's start postulate 2. We've talked about it a little bit, about this idea of measurement. And it's about the idea, the operation, that's a word I'm going to use very carefully here, the act of measurement involves something called a linear operator. So we're going to learn about linear operators today. All right. And we'll see that linear operators are just mathematical representations of experiments or measurements we can do about it. Again, remember that wave functions are a mathematical object, so measurements also need to be a mathematical object, and that object is a linear operator. Let's see what a linear operator is first before we think about what they mean in quantum mechanics. You have played with linear operators in your life. In fact, all of arithmetic is linear operator. Let me show you what I mean by that. So we can define an operator. All right, an operator is a mathematical object we're going to be very specific about it. There's general types of operators. I want to be very specific about the kind of operator we have. Is a mathematical object that takes let's say a object like a wave function, a number, or a function, processes it, and returns the same, and returns a value. Right. So you can kind of think of an operator as a function. It's a generalized function. But you know, as you think about functions in math, functions are things that take in numbers and spit numbers out. An operator is more general. You could, for instance, we'll look at operators that take in wave functions and spit numbers out, or things that spit in wave functions and give you more wave functions. Things that give you, put in vectors, you get vectors out, put in vectors, get numbers out. Okay. So you kind of think of it as a general function. Not exactly like a function, because you guys, if you remember from Algebra 1, functions require specific properties to be defined as a function, right? You have to pass the horizontal line test and smoothness and continuity and all of these things that are in calculus. Operators don't necessarily have that restriction, right? They don't necessarily have to be one-to-one and onto, as they say in math. They can be anything that takes a set of objects and converts it into another set. They're very general. And so let me give you some very simple examples that you guys have done in your past. Right? You can define the plus operator between two numbers A and B or vectors. Right? That's the plus operator. And we know how that works. He takes A and adds it to B. And it gives you a number C. Right? So outputs another number. Right, so the example is plus 2, 2. This gives you 4. Okay, that's an operator. It's an object. The plus sign is an object that takes two numbers and gives you another number out that is in the set of the inputs. Like, this is an important idea. I'm not going to go into too much detail in here, but this is the key thing is that this operator maps its inputs into the same set as its outputs. The outputs and the inputs are shared. So you can think of an operator as something that maps back to itself. So it's not a conversion that takes 2 and 2 and converts it into something that doesn't exist, right? Or you can feed it right back into the input, right? I can take this number and then apply it again. So the range is the same as the domain for this operator. The inputs are the same values as the outputs. Okay. So obviously there are functions that don't do this. There are some functions that you feed in a function that spits a number out, and that's also an operator. Okay. Another operator you guys learn. Of course, multiplication is the other operator. I'll just write that here, right? You can have the times operator, which gives you some value C. 2, 2 gives you 4. Right? It turns out that these are the only two operators on the real numbers. The real numbers are defined with two operations, plus times. Now, you're going to stop me and say, well, what about division and subtraction? Probably not too hard to convince yourself that those are just the inverses. So going backwards, right, you take the division symbol, takes the output and one of the inputs to give you the other input. And subtraction does the same thing, right? It takes the output of the plus and returns you back to the original form. Okay, so minus and division are just inverses of these two operators. So the real numbers only have two operations, plus and times. Okay? So if you know, right, you can define all of real numbers with these two operations. That's all you need. You can get from one number to any other number in real numbers with just plus and times and the inverses. Another operator that you guys are learned is one that takes a function and returns a function. And that's the derivative operator. Right? Imagine you have this derivative operator d by dx, right? That takes in an input f of x, right? And that gives you the derivative of f of x. I'm just going to write it in text, right? And so a good example of that is d by dx of x squared. And the output of that is 2x, right? That maps, it maps functions into themselves, right? You have this, imagine you had this collection of all possible functions. You pulled one out, take a derivative of it, and it gives you another function in the package or in your collection. And it maps it back to itself. Okay. So operators are just mathematical operations. They can be anything, right? But in particular, we want to focus on a particular type of operator, which is called a linear operator, which has very specific restrictions. Right? And so the postulate 2, let me define the postulate now, instead of talking just about operators, is that any observable, any physical property, measurable from a wave function, or an object represented by a wave function, and remember, anytime I write the letter psi, Greek letter psi, think wave function, can be, no, sorry, let me say not can be, is related to a specific linear operator. Okay, so there has to be, if we want to measure position or momentum or deflection, anything you want to do, it has to have some we have to come up with some mathematical object that satisfies the properties of what's called a linear operator in order for it to be something that's measured. So that gives us a restriction on what can be allowed. And the rules of a linear operator are very, very simple. So linear operators satisfy two properties. Right? Imagine you have an operator, a general operator O, and I'm going to write it with a little hat. You write that little hat, think an operator. We're going to see that anytime you, as I said, anytime you write an operator that works, that means it corresponds to a specific property of the system. So we define them based on our measurement, what we want to do. It satisfies two properties. Right? So the first one is if O applied to some wave function psi1, so you have some atom in state psi1, and it returns that wave function back, meaning that the wave function is unchanged, right? That's a measurement. And when we do a measurement, like we talked about last class, it also returns an eigenvalue, right? A number on the side. It takes that vector and multiplies it by some number so that the state is unchanged. The direction is still pointing in the same direction in space, but it's been stretched or contracted by this value A that comes out here. So we'll say that it returns a value A1. I'll give you an example of this in a second. And imagine we have another atom in a different state, psi2, that returns another response for a different state. Okay, so if this is if psi1 is upwards deflecting, and O is our deflector detector, if this A1 is going to be the value corresponding to up deflection, which is +1 in our construction. You'll see that in the homework. If you don't remember from last lecture. And let's say this psi2 is downward deflecting, then A2 is the -1 that you get from a downward deflecting. Those are the readouts of our experiment. Okay, then you can say that O of the sum of psi1 plus psi2 gives you actually, so let me replace that. Let's say, for instance, they're both the same. I apologize. So let's say they both return A. All right, they both return the same value. And O of psi1 is equal to A of psi1 psi2. Okay, so the idea is that if an operator returns a specific value for one state and returns the same value for the other state, then the operator will return A for the sum of the two states. All right, that should seem trivial to you. Maybe not, or maybe not. It's not. Turns out this is not as trivial as you may think. What this is saying is this. Imagine you have some system that has some behavior, okay? And when you measure that behavior, it gives you some answer. Okay? And then you have a completely unrelated system, perhaps in a different state, that gives you the same response on your instrument. Then it says that when you combine the two states together, right? Remember, we can always add states together and make arbitrary states of an atom or a particle, that you get the same response for the physics of two objects. So what this is saying is that you have two single objects that have the same physics, then the sum of those two objects interacting with each other also have the same physics. And this is extendable forever. Let me give you a counter example of where this doesn't work in real life. I think I've mentioned this before, but I'll mention it again. Imagine that psi1 in classical physics, in real life, not real life, macroscopic world, that psi1 and psi2 are planets that are orbiting. Okay? And you take those two planets, those two orbiting bodies, and you separate them as they orbit their sun. Okay? And you say, okay, planet 1 has this orbit, this orbital behavior, we call that A. And you measure the orbit, and you get this value for the orbit out for this atom around the sun. And then you go look at the orbit for the other planet separately, and you get the same thing. They're basically the same planet, same distance. They're just orbiting the sun separately. In quantum mechanics, what it says is that the orbit of the two planets around the sun is the same as if you just added the two single orbits together. In Newtonian physics, Newton's laws, this fails miserably. I don't think it was the other class I mentioned this, but there's a book called Three-Body Problem, sci-fi book about this issue, where if you have an orbit of two bodies, perfectly stable orbit, you can solve for the solutions, no problem. The moment you add another body, which may have the same physics, all hell breaks loose. The physics don't add in a linear way. In quantum mechanics, it adds in a linear way. The physics of one object, if it's the same as the physics of the other object, the physics of the combination is also the same. Right? This is not true in classical physics. It's just not. So already this gives us a simplification, meaning that if we can understand one object, we can understand an arbitrary number of objects with the same behavior. Okay? That's really, really powerful. You can't do that with billiard balls. You just can't. But when quantum mechanics, you're capable, because if you know the physics of one billiard ball, you know the physics of all of them together. Really, really powerful. Okay? So this is a linear object. right? That in some sense, the physics of one object can be appended to an arbitrary set. And I know that seems like a small thing, but it really does limit the kinds of operations or the things that we can measure. Okay, so let's look at some operators today. And so we've looked at, let me go back really quickly. Let me just pull up one more screen. Actually, let's just go ahead and do a quick example. This is just a quick example from the homework. I'm going to do it one more time for you. You can write that the z deflection operator right, which I call in the homework as z, which is in fact the actual label for it. Right, we showed that operators, the measurements for vectors are matrices, and this operator can be written as 1, 0, 0, minus 1. Okay, so there's our operator. Right, that's a representation of our z deflecting box in the basis of up and down deflecting atoms. Right, we have a basis set of potential states. Phi 1, which is the vector 1, 0. We call that z plus, right? That's the deflecting up. I'll call it phi plus. And phi minus 0, 1, which we call the z minus state. Okay, so those are our base states, right? And any wave function is a linear combination of the two. Right? So a general wave function from psi is going to be equal to c1 times 1, 0 plus c2 times 0, 1, where c1 squared plus c2 squared has to be equal to 1, right? Normalization, right? The total probability of anything happening. Okay, so those are our constraints for our system. Any possible combination of those two coefficients that the square sum to 1 is a valid state. Right? Remember, it circles that circle. So let's pick a couple of random states and see what SC does. Just one more time. Right, so let's try phi plus. So we apply SC to phi plus. So 1, 0, 0 minus 1 times 1, 0. We'll go through this math one more time. The best way to think about matrices when you're doing operations with them is that they're a vector of vectors. Right? Like if I say, for instance, I cut it down the middle and I draw little brackets around these two rows, you can see that it's just two row vectors, as we call them, sitting in a little space together. Okay, so vectors can interact with other vectors through the dot product. So multiplication of this is a vector times a dot product of the vectors in the matrix. So let's just work that out. Right, so we get another vector here. One that comes from the dot with a component that comes from the dot product of the top row, and one with the component from the bottom row. So let's go ahead and dot those together. 1, 0 dotted with 1, 0 is 1. Because 1 times 1 plus 0 times 0. We say that those two vectors are parallel. In fact, they're the exact same vector. They're both 1, 0. So the dot product is by definition the product of the lengths. We'll remind you that the definition of the dot product, which is two vectors v1 dot v2, is equal to the length of v1 times the length of v2 times the angle, but cosine of the angle between them. Okay, so if you had two vectors, theta is 0, cosine of 0 is 1. Okay, so the dot product is just the length. The product is the length of the two vectors, and all the vectors are the length 1. Okay, so it's 1 times 1. So we get a 1 here. And we can immediately look for the other one that it has to be 0, right? Because the 1 multiplies the 0 and the 0 multiplies the 1, and everything cancels out. And you don't even have to, in some sense, you don't even have to do that. you know that this 1, 0 is an x vector, 0, 1 is a y vector, and they're perpendicular. That means cosine is pi, theta is pi over 2. They're perpendicular, therefore the dot product is 0. Okay. So what happens? Well, we feed in SC, we feed in phi plus an SE, we get the same thing back. Right. So what I can say is, in fact, is that this is equal to, I can just trivially factor out a plus 1 times phi plus. Okay, so SC measures the state phi plus. It returns phi plus with an additional factor, right, that little eigenvalue of 1, just an arbitrary 1. And we say that that eigenvalue of 1 corresponds to the measurement of an up-deflecting atom. Right, so this is our up-deflecting property. Which is equal to the property of up deflection. Right, our little box reads out a plus 1 every time it deflects an atom up. So let's go phi negative now. One, 0, 0, minus 1. 0, 1. Right? Okay. I don't really have to walk through this math. I think you guys can probably figure it out. Right, we get a 0 on the top and a minus 1 on the bottom. And this is equal to factoring out a minus 1. Minus 1 times phi negative. Okay, so once again, our operator measures phi z or phi minus. It returns it, doesn't change it, and it returns a minus 1, the eigenvalue. Down deflecting. Okay, so that's a really trivial system. But that's the idea, right? We feed in, right? We know that this is a good measurement. We know it's a proper measurement and that these are proper results of this experiment, because when we feed in something that is defined with that state, we get the same state back times an eigenvalue. And that by definition means that it's a proper state of the system. Okay? Proper states of systems, when observed, measured by the operator that they're defined by, should return the same wave function times a value called the eigenvalue. So these are perfectly reasonable functions for this operator. Okay, so that means that we know that this operator, when we feed in plus deflecting, gives us plus deflecting and minus. It's the representation of our system. Let's look at these wave functions now, and you do this in the homework. I'm just going to do it for you really quickly. Let's look at Sx now, the x deflection, using a basis state of z deflection. So let's look instead, really quickly, just a real quick example of Sx times phi plus. Okay, Sx, I'll give you the definition of it in the homework. But that is 0, 1, 1, 0. Okay, that's what Sx is. We're going to minus 1, 0. All right, let's look at how this dots. The top one dots the 0 because the 1 and the 0 and the 1 and the 0 cancel each other out. And so we only get the net way non-zero value we get is the 1 times 1 in the second component. So look what this does. It changes the state. Okay. So SC, when we feed in our Z deflecting states, we get our deflecting states out times the property value. But when we feed in a state defined using an incompatible property, which is Z deflection, and we feed it into the X box, it changes the plus into a minus and the minus into a plus. Right? So this is not a proper measurement. This is a manipulation of the system. Right? And so we can say right here that, right, that Z deflection is not a property of X deflecting atoms, or vice versa. Right? Because the operator that represents that X measurement takes a Z deflecting state and changes it. Right? It's a manipulator. In fact, this is how we manipulate an NMR. Some of you, I don't know if anyone in this class was in my NMR group yesterday, but I gave you guys I gave you the NMR kids a spiel. And the way an NMR works is like this. You take a Z magnet, okay, you put your sample in a Z magnet that causes the Z states to split in energy. So there's not a deflection, but what you do is you cause a magnetic field. One of the states is aligned with the field, and the other one is anti-aligned with the field. The field's up. You can think of the field has an up value to it. And so the up atoms align with the field, and the down atoms align against the field. So they have different energies. Okay, so you create an energy difference between up and down deflecting atoms in an NMR. And then what you have to do to measure spectroscopy on those two energy levels is you apply an X magnetic field to cause the up deflecting states to become down deflecting states and the down deflecting states to become up deflecting states. So an NMR experiment is both operations. You define a system using SC, and then you mix it up with SX. And what happens when you watch the system as it moves in time in the x-axis, as the atoms mix up, they oscillate between up and down, and that oscillation causes emission of light, which is what you're detecting. So NMR or MRI, in some sense, is based on the idea that we have incompatibility between Z and X. We create our protons, our nuclei in NMR. We prepare them in a Z state, and then we mix the Z states up with an X field. And that mixing causes light to be emitted from the system. That's magnetic resonance. It's the basis of MRI and NMR. We'll see that more carefully as we go on. The basis of spectroscopy. Okay, so I'm going to stop with spins and deflections for a second. And I want to change our perspective a little bit. Because, of course, as we'll see, spin and deflection, these rules are very important in chemistry, but there are other important properties we need to measure as well. Right? So postulate 3 is a kind of a continuation of postulate 2. It's going to be a construction of operators in space. How do we define things in terms of X, Y, and Z? That's what we really want. Chemistry, in the end, we want chemical structure. That's really important to us. So we need to have a wave function that's defined in space. What we're going to define are, what this is about linear operators for two different properties. X, right, position, and P, which is momentum. Okay. Now, why do I choose position and momentum? It should make sense why I care about position. In the end, we want to think about where electrons are in our system. That's an X question. Why momentum? Well, the reason why we choose X and P comes from Newton. It's actually the reformulation of Newton. Newton defined his laws based on two properties: the acceleration and the position. F equals ma is a derivative, is a function of time and x. So if you define an acceleration or velocity and a position, you can define the physics of your system. It turns out that acceleration is not a particularly useful number. Velocity is even less useful number because velocity isn't conserved. It's position dependent. Right? It depends on your observer. If I'm running 60 miles an hour that way, 25 miles an hour this way, it looks like I'm running 25. But if you're running along me, it looks like I'm running 0. Right? Velocity is not a particularly useful thing because it's observer dependent. Position and momentum are observer independent measurements. There's something called the conservation of momentum, which means that all momenta can be calculated at any position in any observer. Right, so there are two very good values. You can define X and P. You can define the physics of any a system. This is something that came from two physicists after Newton called Lagrange and Hamilton. Newton was the start, and Lagrange and Hamilton formalized it. So X and P, if we can define X and P, we can in some sense recreate physics with quantum mechanics. Okay, if we have operators for the two important properties of a physical object, then we can go. So let's think a little bit about taking this idea of vectors and converting it into something that's a function of position. Okay, so let's set up a very simple idea, right? Let's imagine I have a giant room. Right? I've got this big single coordinate. All right. Imagine I'm standing on a line. We're in a one-dimensional world. That I can mark by X. All right. And at the far left, I'm going to put a wall. All right. So we don't have to worry about negative numbers. So at X equals 0, I'm going to put a giant wall in the box. Right, an infinite wall. Right, and I'm going to just allow this to go to infinity. Maybe we can be in the room. Let's say that it's this wall, and then on the other side, the door is there. Okay, we're in a room. Right, maybe it's these two walls. Maybe it's this corner and that corner over there. Okay, and let's imagine that I place an atom somewhere in the room. Okay, we're in a complete vacuum. It's not a very useful room. But we have an atom, maybe one electron. Let's just say one electron. It doesn't matter, just an object. Somewhere in the room. Okay, we can't see it. Right? But we want to come up with a box that allows us to measure. Right? To where it is in the room. Okay. So what I'm going to do is this. At different points, equally spaced points, from here to the wall, from the two edges of the room, I'm going to place little sensors. Okay, and every time the particle passes by one of those sensors on the floor, it adds +1 to the tally. Okay, so the idea is I'm taking little electrons moving around randomly, and every time it hits a position, we have a light that appears on it. Imagine we just have like an array of LEDs on the floor. And every time the electron passes by that, an LED lights up. Okay, so I'm going to have some number of positions, some number of sensors, and I'll just kind of mark them randomly for now. We'll just keep them equally spaced. Okay, and what we're going to do, so each one of them is a little detector box, right? So each one can be represented by a matrix or an operator that measures the position. Okay, so I can say that there is an operator or a box at position 1, an operator or a box at position 2, and I'll just kind of dot it all the way to n-1 and exit. Okay, so every time particle, right, those are little LEDs, and they light up every time the electron passes over time. And all you guys are going to do is just count. I'm going to have each one of you sit at each one of these LEDs and stare at it. A bunch of Adderall, so you're super focused. We're going to stare at it for 18 hours, and you're just going to sit there like those people that look at the stop signs or the red lights and see how many people pass by. And you're just going to tally. All right, so we're going to start as the particle moves around the room. We're going to start adding tallies. All right, so maybe Isaiah here at X1 gets a little bit, and then Allison and Henry all over there see a bunch, and then maybe someone in the middle sees a bunch, and we'll see something that looks like this. Okay. So we now have accumulated something that looks like a distribution of position, right? It's a probability distribution. Think about these as grades, right? This is telling you the number of grades for each grade point, and it gives you a distribution of the statistics, right? So this gives me some sense of the counts. Okay, let's remember now, let's define a wave function and an operator for this system using the rules that we have. Remember, we are going to create our wave function, remember, is going to be defined by a set of basis states. So what is our basis state here? Or a basis set? Well, we'll say that phi I is defined to be the readout at each of the points. All right, we'll call this readout to be, let me just give it a label. We'll call it P of X. Okay. So we'll let phi I be of P of X sub I. Okay. All right. So what does we have these outputs for each of the states. Right. This is P of X1 and so on and so forth. P of X2 and so on. But let me ask the question, is this correct? So let's think about that a little bit. These correspond in some sense to the probability. If I take all of the values, let's say I have 100 observations, and Isaiah sees at position 1, 10 of those observations mark his LED, then the probability that he would expect to see the atom at this position is 0.1, right? 10 out of 100 times. Right? So I'm going to put a question mark here. Maybe this isn't the right thing to write. So let's just say that out of an event, X sub I sees N sub I events. So the probability at X sub I is the number of events that Isaiah sees divided by the total number of events. What was the definition of the components of our system? Remember that the components of our vector, the square of them is the probability. So the square of the basis state for that position is not the probability, but the square root of the probability. Remember that the probability, so if we have a wave function, let's just recall that if you have a wave function, sorry, let me change the label, that looks like C1, C2, ... Cn, right, just a bunch of random numbers, remember that the probability of seeing event I, is Ci squared. Okay, so if this is the number of tallies that Isaiah sees, then the component of the wave function is the square root of that number or something. It's not exactly the number. Okay. So what we could say is that P of X1 is equal to some wave function squared. It's some wave function for the state at X1 squared. All right, so what each one of you are measuring is not the wave function of the atom at that position, but the square of the wave function, right? Because that's the probability of observing the atom at that point. So if I construct this probability distribution, it gives me a perspective on the wave function, but it's the square of the wave function. And in fact, it's not only the square of the wave function, but the wave function may be complex. So it's the absolute value squared, the magnitude squared. All right, so what you observe when you measure position is not the wave function, but the square of the wave function, the probability distribution. That's Max Born's probability interpretation that we came up with a week ago. that the square of our observations tells us about the probability. All right, but this gives us a construction, right? You guys have detected information that you can now encode into a description of this system, or at the very least, it gives us a recipe on how to get to the probabilities. Right? We just have to come up with a wave function that when we square it, gives us your experimental results. Okay, so what I can do is, you can imagine now, I can start to fill in the gaps, right, with even more detectors. Right? And you'll imagine what I get is a smooth curve. Right? You're going to have a function that varies in time or varies in space, and it's going to be smooth and infinite. Maybe it looks something like this. I'm just arbitrarily making something up. Right? Maybe it looks something like this. And this is the square of the wave function. Right? What you measure with your sensors is that square. Okay? This gives us a pathway to construct an Xbox. All right, not a Microsoft Xbox, an additional box. I'm going to say Xbox or P boxes as well. We'll talk about for momentum. But this gives us an experimental route. But unfortunately, we lose some information, right? When we do this measurement, we get the square of the wave function. We don't get the actual wave function. So the nice thing is that it does give us an idea of what the structure of this positional response may be of our system, but doesn't give us the full picture yet. But we can start with that, right? We can start to construct things this way because it does give us an idea. All right, so let's look at how this works. All right, I'm going to define now the position operator. X. Okay. So it's our little box. All right, and it's going to be defined as follows. All right, so what we're going to do is we're going to assume now, so what we'll first do is assume a finite number of points that we're checking. So space is discrete. So we can count the number of points in our space. So x1, x2, xi, xn minus 1, xn, right? So we have n sensors. This is like n detectors. The definition of the operator, the position operator, is that the position operator at a given position x sub I, when measuring the wave function of a system that moves through it, which is a function of x, right? The wave function is this thing that's varying in position as we move through the room, gives two results. One, it just gives the value of the position if the wave function is defined at x sub I, and 0 otherwise. Okay, so all this is saying is that each of these sensors on our floor, x sub I, we have a wave function that's defined in the entire room for the particle. It could be anywhere. Okay, and each of these tiles has a sensor. Each is labeled by x sub I. And what it does is it returns x sub I. Right? It's just a ping. Hey, I got something here at x sub I. If the wave function is there, okay, if the particle is right here, this sensor says, hey, the particle's here, and it returns its position. And if it's not there, it returns 0. That's very easy. right? So it's an extremely localized sensor. It only detects exactly what's at the position of that. And so what does the basis state for this look like? Well, we can say that psi x, the way we're going to construct it, is a sum over all the different positions of some coefficient times a basis state, which is defined at each position, so x sub I, where phi of x sub I is the easiest damn vector in the world. It's got n components and it's 0 everywhere except for the ith position. So 0, 0, 0, there's a 1 and a 0, 0, 0 all the way down. And this is the x sub I, the ith position. Okay, so it's exactly the same way as our deflecting results, except now we have n components, one for each sense, instead of just 2 results, right? We can have n results, n steps. So each vector of this system just looks like a bunch of zeros and 1. There's n of them. Okay, and so when we can, now what we can do is we can construct an x operator for all positions in this space. And so in this, the x for our wave function, the x operator is this giant n by n matrix where along the diagonal you have x1, x2, all the way to the xn, and every other value is 0. All right. It's not too hard to show that this gives the right result. What this is saying is that if your atom, you measure your atom and it's exactly at position x sub I, it returns x sub I. Otherwise, it returns 0 elsewhere. That's exactly what we want. It's this big diagonal matrix. Okay. The power of this technique is that there's no more complications. This is completely arbitrary. So the number of points I have. I can make this construction however I want, right? Each one of the positions, each one of the sensors is acting independently. So I can have as many sensors as I want because the operator is linear, right? I have an operator that acts on my wave function that gives me a local result for that position. I have n local operators, and they all return local results. And so the total result is just the sum of all of them. Okay, so I can scale this system arbitrarily. It doesn't have to be n. I get the same physics if n is 10, a million, or an infinity. It's all the same. Okay, so I can just, what I'm going to do now is I'm going to take n to infinity. I'm going to make space continuous. Right, so as n goes to infinity, space becomes continuous. And now our wave function, which is an n-dimensional vector, is now an infinite dimensional vector. It's got a value for every point in space. It's just a function. So space becomes continuous. And now our wave function, psi of x, is also a function. A smooth continuous function. It's not a vector anymore. It's a function. We can talk about it like a function now because it has an infinite number of a continuous set of values. No gaps. There's no discrete. Every value, every real number has a sensor. Every position. Right. So this is where the powerful thing comes in, right? What we're going to do is we're going to say, let's define a basis set for our object that is local in the position. What we're going to say is that whatever the atom is, who knows? But what we can do is define its probability of being at a certain point. And that gives us an operator that allows us to measure the position that's very trivial and gives us a construction, somewhat of an abstract construction, that allows us to define the probability or the behavior of the object at any position in space. Right? Again, this is just a trivial construction. I've just made a choice here. I've made the simplest choice possible to take a vector and encode it into a space. X, Y, Z. Just make each position in space a component of that vector. And they satisfy all the properties, right? That the length is 1 and so on and so forth. And we'll talk about that, those properties. So, of course, the question that we have to answer now is that, let's say we have this electron now. We're not talking about its deflections at the moment. We're talking about its position in space now. That's our experiment. What are the compatible measurements? What are other things that we can define? We can define its position. What else can we define alongside of its position? And that's a totally valid question, because in classical physics, when we do Newton's laws, there are two parameters, the position and the momentum, and they're compatible with each other. All physics can be defined by the positions and the momentum of the objects involved. So we've created a we've created a position operator that measures position. Can we also create a compatible momentum operator to measure the momentum of it? If we could, then we recreate physics in some sense, right? Because Newton says that we can do that. Can we do it in quantum mechanics as well? Lost my notes for this. All right, so what about momentum? I just want to make sure I have the right notes for this. This is a very careful argument that Heisenberg, in fact, makes. And what I'm going to prove to you is that, in fact, unlike Newton's physics, momentum and position are not compatible in quantum mechanics. We fail that one thing that we get in quantum mechanics. It's going to be hard for us to appreciate why it fails just quite yet, but we're almost there. I want to show you what that means, that it fails. And I have a really nice drawing. I just want to make sure that I get it right and I don't screw it up for you guys, because it's a little complex. Just find the right notes. Yeah, here we go. Okay. So what is momentum? All right, so let's go back to quantum, or to classical physics. The momentum is a vector, right, P, which is equal to the object's mass times its velocity. Okay. All right, this is conserved. Momentum is conserved. This is why we use momentum, is it's conserved in space. Right, if you have, the idea is that if you have two objects, M1 with V1 and M2, V2, and they collide to have new momenta, M1 V1 prime and M2 V2 prime, right? They collide. Then M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V2 prime, right? The momentums are conserved before and after. Okay, that's why momentum is so useful, is because unlike velocity, momentum is conserved. Velocity is very much not conserved. It's probably not hard to see that. Imagine hitting, for instance, a wall with a car. very clear that the velocity is not conserved because the car hits the wall at 80 miles an hour. The wall does not start moving at 80 miles an hour, but the momenta are conserved. The momentum is useful because of that conservation. And because of that conservation, we can talk about momentum in a universal and agnostic way. We don't have to worry about the observer or how the observer is moving. It always is conserved. All right, so we're going to do the same idea, right? We're going to instead have a speedometer, a momentum meter. And we're going to do the same exact thing. We're going to have a particle flying by us back and forth in the room. And every time it passes by our speed gun, it's going to read out the momentum. Right, so our experiment, each one of you is going to hold a radar gun at P0, P1, P2, and P3, and we're going to say increasing momentum. Right, you all are going to sit in a room, and let's say Isaiah is looking for something that's moving at 1 meter per second, and maybe someone over here has one that reads things that are only moving at 90% speed of light, or something like that, right? So you have different momenta, different triggers, and every time that particle passes by, and that particle has that momentum, it pings. Right, and we see that the particle has some momenta. Sometimes it's slow, sometimes it's fast, sometimes it's in the middle. It depends, right? Some choices. All right, and so then what we say is, okay, let's define a momentum operator, right? But let's treat the system, right? Let's use the definition of position, right? We've defined our particle with our sensors. We're measuring it with our sensors. Okay, and so we have a wave function in terms of space, psi of x. And what we're doing is we're feeding that thing that we've measured with psi of x, that electron, and now we're measuring it with our gun. Okay. With our radar. So what I could ask then is, what is now the momentum operator? We measure a wave function psi of x. Right, so this is our electron with the position that you all measured, and now I'm going to measure its momentum. Right? When I measured the position, right, all it did was return the position. Right? It gave us a diagonal matrix. It said if the atom was at this position, the sensor will return the position. Otherwise, it doesn't return anything. So then you say, okay, well, is that true for momentum? If I ping my particle psi of x with my momentum box, does it also return just the momentum that it's at? Right? That would give me a diagonal matrix. And that would mean if they're both diagonal, that means that that psi of x is a basis state for both of them. They're compatible measurements. One's diagonal and the other one's diagonal. Works fine. Not too hard to show that math. Unlike SX and SE, if you remember, actually, let's go back for just a second. I just want to show you this structure really quickly. Remember, if we notice in SE, remember our systems, our basis states are defined by their z deflection. And so the matrix reflecting z deflection is diagonal as well. There's zeros on the edges and non-zero values on the diagonal. And what that corresponds to is that the basis states are unchanged when you measure them, meaning that this is a basis state for this measurement and it's compatible. What that also means is that every other compatible measurement set in that basis is also diagonal. Because here's an example of one that's not diagonal in this basis. And what did it do? It took a vector and changed it to another one. Okay, so for measurements to be, if we represent them as matrices, if we define them all in the same basis, compatible measurements are all also diagonal. They all have to be diagonal. So if momentum is not a diagonal measurement, then that means that it's not compatible. X. So what we would expect is that momentum, when we measure the momentum of a wave function at x, it just returns the momentum at that point, pi. Unfortunately, that's not what it does. So this is what Heisenberg and I think Heisenberg is the person that came up with this. Yeah, I think it's Heisenberg. He comes up with a solution to this problem. He says if you have a wave function defined in this position, whether it's momentum, operator resolve this. It's not diagonal. I'm going to do it in yellow so it's nice and clear. But you get a very strange result. It's complex. You get an imaginary number times the derivative operator applied to psi of x. All right, times this new number we haven't seen yet, h bar. This is a constant that we haven't seen yet. And the reason why is because the way I've introduced the material, we haven't talked about h yet, but this is a really complex number. But we get a new constant. But the important thing is we get an I here. And we take a derivative. So very clearly, right, psi of x, when we apply p to psi of x, we don't get psi of x back, we get the derivative of psi of x back. Right, so that means that this changes, right? This means that this, by definition, is not a valid measurement for a system defined by position. Because we don't return, we manipulate the state. We take the state, when we feed it into this box, it takes the derivative of the state and multiplies it by a complex number. Right? So we have, and remember that properties need to be real. Right? They need to be real properties. They have to be real numbers that get spit out. Here, this is by definition, if psi of x is real, then this is complex by definition. Right? A real positional wave function has a complex momentum. So the momentum in some sense is undefined. So if psi of x is real, I'll just write that here. Real means that the momentum is complex, imaginary. Okay? This is by definition incompatible. X and P do not mix. In fact, what you can say is that you can prove this even further. The more you define a state based on its position, the less you know about its momentum. They're inversely proportional to each other. As maybe you've heard this term of Heisenberg uncertainty. Heisenberg uncertainty principle says this: if you have some uncertainty in your position, meaning that, remember in our momentum box, our position box, in our position box, we know the position exactly. Right? Every point gives you an exact reading of the position. So at each point, we know exactly when that electron is there. We know the position exactly. And what it turns out is that if you know the position exactly, you know absolutely nothing about the momentum. If your error on position is 0, the error on your momentum is infinite. It's undefined. What that means is that a particle that is perfectly defined at a position. Imagine I freeze the particle at x, and I know that x is certainty. That means its momentum is entirely undefined. It exhibits all possible momentum. It can be moving at the speed of light. Well, it can't be doing that, but it can be moving near the speed of light. It can be at rest. You don't know. It exhibits all possible momentum if you know the position exactly. And vice versa. If you define the momentum of an object exactly, you know nothing about its position. So these are inherently incompatible measurements. And I'll say that really, really strongly, and we'll finish off there. Momentum defined, position undefined. They go hand in hand. And vice versa. Now, why is this relevant? My last statement. Why do I care about momentum? Well, let me ask you, why do I care about momentum at all in chemistry? Because when you think about momentum, you think about building balls down. Of course, there is some of that in chemistry. We do collisions and reactions. Of course, that matters. But when we're just talking about electrons bound to atoms, do I really care about the momentum? Maybe not. But the question is, what can I calculate from the momentum? If I know the momentum, what else do I know about the system? And the thing I want you to remember is remember what we do in chemistry. Remember that the important way that we define our atoms is through orbitals. Orbitals are states for the electron of fixed energy. The 1s electron always has the same energy. 2p electron always has the same energy. They're defined based on their energy. Energy is directly connected to momentum because kinetic energy turns out to be p, once we do the math, p squared over 2m. So in order to know the energy, you need to know the momentum. So if we want to calculate states for the electron that have fixed energy, we have to calculate states of momentum. We have to choose a momentum basis, an energy. And that is, and by definition, incompatible with position. So what do we get in chemistry? We get a series of orbitals, 1s, 2s, 3s, so on, that have fixed energies, fixed momentum. The electron of the 1s orbital has a fixed energy by definition. Well, what does it not have? A fixed position. Because we get orbitals, right? What do orbitals are? They tell you this delocalized shell where the electron may be. You have no concept of where the electron is. You just know it's somewhere in this region. So we define the position exactly. Sorry, not the position, the momentum or the energy exactly. And the trade-off is that we get this wave functions or states of position that are completely undefined and delocalized. There is a most probable place for the electron to be in the 1s orbital, but it can literally be anywhere in space. More likely spots than others, but in some sense, a hydrogen in this room, the electron can be on fucking Mars. There's nothing stopping it from being on Mars. Because the momentum is defined exactly for that 1s orbital, and therefore the position is. You guys have seen this before, you just haven't had an appreciation for it yet. All right, so that's the idea. So what we need to do now is to say, well, we have to make a choice. Do we care about position or do we care about energy? And what we're going to do is we're going to care about energy because that's what matters in chemistry. Well, we talked about energy last semester for a whole semester. So what we're going to do is we're going to choose one of these different things and play around with them and see how we can go from there. Okay, so that's what I have for you guys today. Have a good one, guys. We'll talk more about this complex number thing next class too. I know that's confusing.